It's a distributed database, and it's been strictly combined with distributed, usually running in the cloud or with multiple servers. You don't run just one. Cassandra's a team of servers. The problems that it's solved are handling data workloads that are closer to your user, the closest as possible. It's not a backend service like Spark or something like that, where um, it doesn't do analytics. It's meant for transaction workloads, and massively distributed. The three things that we built it for from the beginning and that we've stuck to is horizontal scalability, linear horizontal scalability. So if you need more, you just add another node and that's all online. Multi-data center, which was a hard problem. It still is. Most databases can't do it. And that is that you have one cluster that spans the entire world and it's all active, active, active. And the third thing is just unbeatable resilience and uptime.
On this episode of Alexa's Input, I'm happy to welcome Patrick McFadin, an expert in the world of distributed databases and a passionate advocate for open source innovation. As the principal technical strategist at DataStax and a leading voice in the Apache Cassandra community, Patrick has spent years helping developers harness the power of Cassandra to build scalable, resilient systems. With experience in software architecture and engineering, Patrick is here to share his insights on the evolution of Cassandra, its role in powering some of the world's most demanding applications, and what the future holds for distributed databases. Patrick, welcome to the podcast. It's an honor to have you on.
Thank you. Yeah, I'm happy we can talk about this. This is one of my favorite topics.
Amazing. Okay, perfect. So, first I want to start with your Korean background. Can you just tell me a bit about how you got into tech and how you got into Cassandra and databases and everything?
I'd like to tell you that I planned it all, but I did not. No, it's funny how people fall into things, and I'm just another example of that. I mean, I really started in tech really young. I think I went to my first computer conference when I was 12 or 13, in San Francisco. It was a brand new Moscone Center. It was 1983, and I went to a conference because I wanted to talk to Steve Wozniak, and so that was the bug that got me. But I took a detour. I joined the Navy for a while and got really into like this idea of distributed computing, and it's funny because I was like, oh, I didn't think it was a thing at the time. So when I worked on communication between ships and things, and that was really cool. And I was like, oh, that's really neat. And I promptly forgot about it. And when I got out of the Navy, I went to university and was thinking, oh, I'm going to be a hardware guy. Like, I love chips, right? Chips are cool. But I kept coming back to distributed computing. I was working on agents in 1995 as an undergraduate, and they didn't work, by the way. But again, I was going back to distributed system problems. And that was about the time the first dot-com wave hit in 98, 99. And so I was back in San Francisco doing that whole thing. And by the way, I will write that book someday. It was crazy, but not for this podcast. But when the bubble popped, I went back to infrastructure and was trying, and really, this is when we really got serious about the internet. And it was clear to me that the problems that we were trying to solve at scale, because we were going from hundreds of users in 1999 to thousands, millions, tens of millions, hundreds of millions, billions of users throughout the early 2000s up to 2010. And in that time, you realize everything is a distributed system problem. And it's probably a data problem. And that's when I first started getting involved with like really hardcore distributed data systems like Cassandra.
Nice. You have me intrigued with this book idea. I guess maybe we can do another podcast about that when it comes out. But
Oh yeah. No, I
Mm.
I will write. There's two books I need to write. One of them is kind of a play-by-play, I was there when it happened.com story. And the second one is a story about Silicon Valley. And this is the one my daughter keeps wanting me to write. She works at a bookstore, so she loves these kind of books. Um, it is a book about Silicon Valley and how such major decisions are made with just so few people. Like
Mm.
a small group of people at a conference going, "Oh, let's do that." Okay. Yeah, it happens a lot. Yeah.
Yeah, would you say that's still mainly how it's happening?
Yeah. Oh, yeah. Every
Yeah.
day. every
Yeah.
day. When you think this AI thing happened because a lot of people got involved, no.
Yeah. Yeah.
A small group of people were like, it'd be cool. Yeah.
And just on that question, what would you propose is a better way to do it?
I don't know if there is a better way. I'm into natural systems. I think that things happen, and it's better when things happen organically like that. It doesn't mean that it ends that way, but when it starts that way, I mean, there's plenty of things in my Cassandra life that started out with one person had a wild idea,
Yeah.
and what's cool about it is if everyone gathers around and joins in the chorus instead of just having it a single person doing it. Um, that was Redis, by the way. Redis was Salvatore jamming on Redis all the time. Do you need help? Maybe. But yeah, I think it works because if it's a community thing, then offering an idea and then so much happens around it. That's pretty
Yeah.
cool.
Yeah, that is pretty cool. I agree with you. Well, I'm looking forward to reading those books for sure and having you back on to discuss them then, maybe.
Yeah. Book tour.
Exactly. So maybe can you talk about a few of the pivotal moments in your career that influenced how you developed this passion for distributed systems and databases, like how you got into the open source community?
Yeah, there's one that stands out specifically. I was working at a company called Hobson's, which probably no one knows about, but you do know about some of our products. We were pretty much running all of the online college applications in the US in the 2000s. And one of those was the Common App, um, which was a very popular because there was like 400 universities that ran it. Well, there's this particular problem we had where if decisions like when Ivy Leagues especially issued their decision, like if you got into the university or not, they all did it at the exact same time. It's like a 5 o'clock on March 16th or something like that. We called it March Madness. Um, and it was this crazy, like completely designed thundering herd problem. And it wasn't, and they did it on purpose because they all did it together at the same time because they didn't want to have it like after someone else. They're competing against the same kids that are trying to get into university. So, all right, there you go. So what would happen is I would have a situation where I'd have 70,000 people clicking on a link at exactly the same time. So we had to build systems that would survive about 5 to 10 seconds. And that's it. And we were running it, I think we had originally had it running on SQL Server, then we moved it over to Oracle, and it was just a March Madness problem. What I wound up doing is I figured this is not a single server problem, and I applied some distributed systems thinking to it, and we wound up distributing a lot of it out over Cassandra. That was my first shot with Cassandra because somebody
Oh,
said, "Oh,
interesting.
I had friends at Netflix that were like just starting to use Cassandra, and they're like, yeah, you should try out this database. It's pretty tough." And so we distributed it out, and it was the first March in 2011, the first March Madness. We never had a moment, not even a little bit of downtime.
Oh, amazing.
And yeah, that was it's amazing now, but in hindsight, but I was sweating it because I'm like, well, you kind of make a risk. And it was very early days for Cassandra, so it was hard to say that if it would even work, but it did. And 70,000 kids got figured out if they got rejected or not. And with no delay.
Great.
Yeah.
What were some of the other solutions that you were considering at that time? Do you
Well, we
remember?
were just trying to think about how we could not use a database. That was the solution.
Yeah.
And that was the problem is databases are always a bottleneck because they're a single point. And
Yeah.
up to that point, to that point, and this is what got me into thinking about distributed, is that we were running databases as a single point of failure consistently as a matter of practice and architecture. And that and it was funny because we were distributing web servers, we had load balancers from F5, we had all this stuff that would distribute the load, except if you looked at the diagram, it would all funnel down to one little single thing, database. And the joke, at least at the time, was, Oracle will scale right up until you run out of money.
Hmm.
And we were buying ridiculously huge servers to just try to scale vertically. And that wasn't the choice. So that's that, and I think that's just a really good practice for any engineer is to look at the status quo and always ask if there's something better because there always is. And that was the moment.
Yeah, I like that point. So I guess so then you got into the Cassandra open source community after that, or
Mhm.
and then did you just like keep bringing it to other things you're working on as well?
It was a matter of looking at because I'd been using a lot of Oracle at the time, and that was a good choice to make, by the way. If you were becoming if you were an expert at Oracle, you were very well employed, and it wasn't a
Yeah.
bad choice. But it was me looking at the future, and this is always worth evaluating too. It's like me looking at the future and seeing this database and this what it was, and I believed in the architecture because I felt like I understood it, but the simplicity and the way that it worked and everything, I just said, you know what, I'm going to put more effort into this. And so I did. I started doing more community talks. I did some
Hmm.
data modeling talks and just started participating in the community, doing meetups, just because I was like, this is really interesting. I want other people to know about it. And that's I kind of got pulled into this community effort. And that's the best part of community is when you find people that are like-minded and we're all
Yeah.
excited about the same thing. So that's how I got pulled into that complete ecosystem.
What has changed since you've been brought in? So you said 2011. That was uh 14 years ago now. I'm like, what year is it?
Yeah,
Um,
2025 it just happened.
yeah, I bet a lot of things have changed. What are some of the main things that you've pushed for and some changes there's been in the Cassandra community?
Well, the two biggest changes, I mean, 2011, it was just absolutely bananas because if you said the word NoSQL or non-relational database, there was 1,000 choices, and I'm not even kidding. I mean, there was so many choices, and some of them were very similar. Like Cassandra is not the only database with that type of architecture, the
Hmm.
Dynamo-based architecture. There are others like React and Voldemort. Yeah, these are all names of databases, and Tokyo Cabinet. These are all weird projects. So it was just it was hard to even concentrate because there was so many choices, and that's
Yeah.
changed. There's been a lot of consolidation. There's really only three or four NoSQL databases out there now that are mainstream. The rest have all kind of faded away. But the second thing that's changed quite a bit is just the maturation of the community itself. Like the team of people that are building the software are so much more professional in the way we manage a project that isn't really it's not a company. And
Hmm.
that in the early days it was a very what would I call it, a little more cowboy, just like
Yeah.
individual effort. Like somebody would just show up with a feature, merge it in and say, look at what I built, and it was no planning. Any planning was basically done on IRC at that point. Now it's much more professional. I mean, we have formal processes to go through, and it's, like, hey, I want to do this, and I propose this, and then we vote on it. Oh, it's so neat and tidy. It's just kind of makes me sad for the old days.
Yeah, pros and cons, right? Uh
Yeah.
sometimes like the being a coding cowboy is kind of fun. But yeah, I guess a lot more people are depending on it now, so it definitely needs a bit more process too. Seeing that growth
Yeah.
is probably pretty cool.
It was fun. I mean, and there's still plenty of that going on. It's
Yeah.
just it's harder to change the project without going through the planning committee.
Yeah, I bet. So Cassandra is a part of the Apache Foundation, the Apache Software Foundation. I'm more familiar with a lot of the products in the Cloud Native Compute Foundation, which I know that you're also a part of. Can you
Mhm.
explain to those who maybe don't know what is the Apache Software Foundation?
Also known as the ASF. And if I think most people are familiar with a very popular license, the Apache license V2, which is pretty popular for just you can use it. You don't have to be part of the foundation. But the foundation is a nonprofit that was set up many years ago, like 1996, I think, and it was there as to create some sort of infrastructure and governance, some way to create a third party so that you limited the amount of control. And then at the time, you think of the problems where there were big software companies like Microsoft that could just unilaterally make a choice and change things for you. And if you
Mhm.
didn't like it, like for instance, they could invalidate a version and make you upgrade to the latest version and pay
Yeah.
for it. So the Apache Software Foundation as a entity now owns the software. They own the license, and so that it's held in trust. And so there's a lot to go with it. There's a lot of ups and downs. It's harder to work inside a foundation sometimes, but it's also much more it is psychologically safe for especially for organizations because they don't feel like, oh, someone's going to take it over or kill it or something like that. And lately with a lot of projects, open source projects, and I'll put that in scare quotes, um, they changed their license. Like, oh, we're no longer going to use Apache license. We're going to use the business source license.
Mm-hmm.
That will never happen in the ASF because the ASF owns the code and they're going to use the one license.
Yeah, that is nice. So what Apache has quite a few products. Um,
Oh, yeah.
what is the main difference, in your opinion, between CNCF and ASF?
Yeah, ASF is an independent organization that provides infrastructure and governance as a service. The LF, Linux Foundation, who is the umbrella over like CNCF, it has a similar mission in a lot of ways. Where they're trying to keep code in the public trust, but the LF is much more organized around using community as a service, I would
Mm-hmm.
say. So they do a lot of conferences, tons and tons. Yeah, LF events is a whole thing, and
Yeah.
they do a lot of conferences like KubeCon, Cloud Native Con, Open Source Summit, etc. So it's a different vibe completely, and there's a little bit more of a commercial entity to it, like
Mm.
companies pay into it. There's a membership. That's what funds all these activities. So it's a little more commercial friendly in that regard. But the end result is you still get open source software that's
Yeah.
available for you to use for free.
And you're also involved in the Linux Foundation as well, right?
Yeah, you don't get in this industry for very long before you're like in all of them. Yeah, I've been involved. I was in the TOC, a technical oversight committee for CNCF for a few years, and then yeah, I've been pretty involved in the Kubernetes world. I did write a book about that though. So I have a book about running data in Kubernetes and cloud native data in Kubernetes, and so that world crosses over with mine quite a bit. Infrastructure is infrastructure. So,
Yeah.
but yeah, and I enjoy both. I enjoy both.
And do you run Kubernetes, Cassandra on Kubernetes at work as well?
Our Cassandra as a service, Astra, is
Yeah.
100% Kubernetes.
Oh, nice. Amazing.
We probably run about 30,000 clusters, I think.
Wow. That's pretty good.
Yeah, we have a
So,
massive Kubernetes footprint. Yeah.
so on that, I don't think we've actually talked about what Cassandra actually is yet. Do you want to give an
Oh
intro to
yeah.
people who don't know? What kind of database is Cassandra? What is it good for?
You're right. We probably should explain that. Yeah. It sounds amazing. What is it? Yeah. So Apache Cassandra is a NoSQL database. It's a distributed database, and it's been strictly combined with distributed. So you're usually running in the cloud or with multiple servers. You don't run just one. Um, it, Cassandra's a team of servers. But the problems that it solved are handling data workloads that are closer to your user, the closest as possible. It's not a backend service like a Spark or something like that, where it doesn't do analytics. It's meant for transaction workloads. So and massively distributed. The three things that we built it for from the beginning and that we've stuck to is horizontal scalability, linear horizontal scalability. So if you need more, you just add another node and that's all online. Multi-data center, which was a hard problem. It still is. Most databases can't do it. And that is that you have one cluster that spans the entire world and it's all active, active, active. And the third thing is just unbeatable resilience and uptime. It's really hard to kill a Cassandra cluster. And that's probably been the thing that people love about it or need the most, especially whenever they're looking at something very difficult to hold up to. Cassandra is, if every database in the world fails, Cassandra will probably be the one that will make it.
Okay, so a few things to dig into. First, why NoSQL, or what does NoSQL mean and why?
Yeah, so the NoSQL started out as kind of this, like, how do we describe or categorize this thing that we built? And SQL databases were the mainstay. MySQL, of course, and Postgres a little bit, and Oracle all over the place. Those are still very popular choices. SQL Server, all of those choices had SQL, and those are relational databases. Another way to describe NoSQL is non-relational. So, and it's only because there's a few different databases that would fit into that. And like Mongo, for instance, is a document model, so it uses JSON. And Redis uses a key value pair. And Cassandra's tabular, but it doesn't do joins. It's only tables of rows and columns. So there, if you're doing an SQL statement with a join in any of those three databases, you will be very disappointed because it won't do that. And that's actually a design choice we made, because that is a joins and things. There are features in an SQL database that we are trying to avoid, and things like those complicated coordination problems, when most people don't even need them. Why even have them in there? So the NoSQL name stuck. And it's funny because it was actually created by one of the committers to Cassandra. He gave a talk at Berlin Buzzwords like in 2010, and he had a big SQL with a no sign through it, and it's stuck. Yeah, Eric, if you're listening, shout out.
That's a great story.
Yeah.
So I understand that some database have blobs like JSON, some key value. A lot of caches have key value. But what does tabular mean?
Tabular is like what we expect from like an SQL database, where you have a table, like you have a key space that holds tables, and the tables have rows and columns. So you select column from table where some predicate, and I just described exactly how you pull data out of Cassandra. So rows and columns are what developers somewhat expect. The difference, of course, is that you're not going to join those tables together. So it's very organized around this denatured, or denatured. That's not a protein. Yeah, it's around the how you take the normal form, so denormalize, like relational databases have like first form, normal form, second normal form, third normal form. Those of you who had to go through that hell in college, the relational algebra, you remember all those. Well, there are no normal forms in Cassandra. It's just all denormalized. And so, but it's still a table of data, so that's why we call it tabular. It's something that we really try to make sure that people don't say is columnar, because that's more in an analytics workload. And those are like ClickHouse, for instance, uses a columnar. And I'm sorry
BigQuery.
for this industry for making
Yeah.
it so crazy and hard.
Yeah, I think I use Columnar with BigQuery quite a bit before for analytics platforms. That makes sense.
Yeah, it's really purpose built for those kind of like aggregation queries, like how
Mhm.
many things happened yesterday, and columnar
Yeah.
is really good for that. Yeah.
So, what is the access pattern for someone trying to use Cassandra? Why is it that, or how do they have to shape their data so that they don't need joins like maybe you would in a SQL database? Why are they using Cassandra and how?
Yeah, so the simple way to describe it is you always have to use a primary key, and the primary key
Mm.
usually consists of a partition key, what we call a partition key, and that is more or less like the identifier of that row of data, and then with some clustering columns which pulls it together. So the underlying data model is actually storing it linearly on the disk. So this is just a representation the CQL, the Cassandra query language, uses, but it always should have a primary key. An anti-pattern would be something where you don't use a primary key and you just create an index on a column and you just do that. So the reason you want to think about this is if you have 1,000 nodes cluster, and there's plenty of those out there. If you do a non-primary key lookup, it will have to go look at every 1,000 nodes for that data. It could be there, right? Maybe,
Mhm.
maybe not. When you use a primary key, then it's like using a zip code or a postcode, because
Yeah.
then that primary key goes exactly to a node that has the data, and then it knows. And so in that 1,000 node cluster, it's just going to one node, and then it'll pull in the rest of the data. So that's how you can get a 1,000 node cluster to be performant within milliseconds. It's the trick.
Nice. So it has some table of mapping, and then it uses that map to go to the correct node.
When you create the cluster, and this is part of that simplicity. When you create the cluster, every node is responsible for a range of tokens, and those tokens
Okay.
map to a partition key. And that's the negotiation. It is done online. So if you have a 4 node cluster, every node is responsible for 1/4 of the data. And then if you add a new node, like one node, then every node is now responsible for 1/5 of the data. So, and so on. So if you add 100 nodes, every node's worth has 1/100th of the data. And the way they coordinate is when you add a new node to the system, it says, "Hey, I'm here," and everyone's like, "Awesome, welcome. Here's your range of data." And this is like a online process that happens during the join, and then after that, it's done. No more
Hmm.
coordination needed.
Awesome. And so, in your time working on Cassandra, has there ever been any interesting issues with this coordination or token matching?
Oh yeah, of course, and usually a user generated. And I hate to say
People are
like, "Oh, you're
usually the
doing it
problem.
wrong." Yeah. It's typically the problem where you don't think about that, and you do, like, you can manually assign token ranges, and let's go back to those cowboys we were talking about, like, oh, I know better, and so you create the wrong token ranges. Or one of my favorites was, this somebody created token ranges so that all of the data was on one node in a 10 node cluster. Yeah, that did work. And these are simple problems, and this is probably what gives Cassandra its reputation, and it does have a reputation of being a very hard system to figure out. But once you get there, and that's probably why when you go to a Cassandra event and there's a lot of people that use Cassandra, they have a bit of a swagger because they
Yeah.
figured it out.
Yeah.
And you know some people, Alexa.
Yeah,
uh,
for sure. But I mean, these are, I think some of the most interesting problems are data problems. So, I mean, maybe it's a little bit earned. It's pretty cool to figure those out, I think.
yeah, that's the thing's always been your first 2 weeks with Cassandra is your worst.
Yeah. Were they your worst, the first two?
Oh God. Well, considering I was using Cassandra like point 0.7, I had a lot of bad 2 weeks.
Yeah.
But yeah.
Do you think now, as it's grown and the community has grown, that that time is shrinking? And like, are people making it easier to use? Like, are you more towards letting people have more freedom and configure everything themselves, or do you have more safeguards now against doing things like what you just mentioned, setting up all the tokens to go to one node out of 10?
We have a lot of safeguards. And of course, we've learned over time. We're also, I mean, in the open source project, we are also very libertarian in a way. I guess that's
Hmm.
the word I'd use, is we give you enough configuration to completely ruin your whole day.
Yeah.
Um, but it's just like with this, great power comes great responsibility. There are guardrails, there are things that are built into the system, and most of this is around ecosystem, like how you deploy the system. For
Yeah.
instance, we have Kate Sander project, which helps people deploy it in Kubernetes, and there's a Helm chart, and it does a lot of things for you. um, Using Docker, for instance, is another choice. An image, a Docker image.
Hmm.
And then services like what we do at DataStax with Astra, where you don't even have to manage your own Cassandra. Um, so there's a lot of choices, and a lot of it is ecosystem. Um,
Yeah.
yeah,
You mentioned Astra a couple of times now. Can you explain what Astra is?
yeah. What's the relationship? Well, so I work at DataStax, full disclosure, and we've been Cassandra users and experts and all sorts of things. I've worked here for 13 years.
That's amazing.
Imagine that. But Yeah, so we've had downloadable versions of Cassandra, and we've done consulting, Cassandra consulting, etc. Years ago, we were like, you know what, we could probably run this better ourselves, and it was a good thing for the community. I think everyone was really happy when we started running a lot of Cassandra our own self because we got it. And
Great.
because um, it is kind of hard to run, but yeah. So Astra is a Cassandra as a service. It's not a uh, it's not a version or a clone. It's actually running Cassandra, and we've done some things to Cassandra in a cloud native way, like the way we deployed in Kubernetes to make it a lot cheaper to run and a lot easier to run. But essentially, it's just giving you a full version of Cassandra that you don't have to manage yourself.
So, what are some of the ways that you're seeing people use Cassandra in the real world? What are some of the queries that they're making?
Yeah, well, I mean, I like to tell people that you use Cassandra every day and you don't even know it.
Really?
Every single day. If you have an iPhone, if you have an Android phone, there you go.
That's pretty cool.
Um, it is cool. And streaming services, e-commerce, it's like I had mentioned before, and this is a general pattern, is Cassandra is best closer to your customers.
What do you
Because
mean by that?
what I mean by that is you want it to be closer, meaning that you want it to be involved in the critical path for your customer, like where you don't want them to have downtime or latency.
Mm-hmm.
And it also means don't put it in the back end. Um, nobody puts baby in a box. But yeah, it's not a back end database. It's so by putting it in front, I'll give you an example. When you go to walmart.com,
Mm-hmm.
that experience that you get is fast and performant and resilient because of Cassandra. And, they run a lot of Cassandra there and they keep it close to their customers. Apple's another good choice too, because all of iCloud runs with Cassandra. And that's a super critical service for Apple. Like you take a picture, you want it to be saved. If you send an iMessage, you want it to go through. Um, and so like the next hop from your phone is probably a Cassandra database.
What is it putting into the Cassandra database? For example, if you're taking a picture.
Your picture. Yeah, it takes the bits, breaks it into chunks. And they have really interesting algorithm. They talk about it a little bit from time to time, but yeah, it's all the data. It's like your iCloud photos and things like that. So that's pretty critical. I'm like, thanks. I don't want my kids to get lost. You think about like what is in iCloud at this point? That's yeah, your banking information. Who knows? Notes. All my great recipes are in notes.
Yeah.
So
So
yeah,
all of your text messages are being put in Cassandra too.
yes.
That's
Yes.
amazing.
That was one of the first use cases there. They talk about it. It was like that was actually the thing that got them on it was very early days of iCloud. They had an some sort of an outage, but the only thing that didn't go offline in iCloud was iMessage. And like, why? And the guy that had set up the Cassandra cluster to run it was like, because I'm running Cassandra. So
But why is that? Why was Cassandra so resilient to the outage?
because it was running across multiple data centers. So and this is a kind of a uptime 101 thing that is really critical for engineers to understand is that, failure happens all the time. There is no such thing as infinite nines. And so whenever you're building a system, you have to weigh things out, like cost versus, the risk. And, if it's your back end office app that collects, money from your office pool, then yeah, that's not a very resilient thing. But if it's something like iMessage and that's the most critical thing for your app,
Mm-hmm.
this is something you want to consider. Like, do we want to run this in one data center or two? Data centers are tough. They can put up with a lot of abuse, but geographically distributing your data is the best way. And getting 3 copies of it is statistically the closest you're ever going to get to infinite uptime. We do a Cassandra survey. I'll just give you some proof. And this is on our Cassandra web, cassandra.apache.org. We do a survey, an annual survey. And I always ask the question, like, what's the longest uptime on a Cassandra cluster? And the average is somewhere around 4 years
Wow.
and continuous uptime. But the outliers are 10, 11, 12 years. of continuous uptime on one cluster. And it's just because they're using just massively distributed data. It's like around the world. So I'll give you an example of like, and this is real world. There was flooding in Manhattan, took down a ton of data centers.
Mm.
The companies that were using Cassandra were fine because they had another data center in Iowa, which was fine. So it's just planning and thinking about it. So this is kind of rewind back to the question. This engineer had done this because they had multiple data centers. They needed distributed all that data across those. And whenever they had an outage in one data center, it didn't take down everything.
Yeah, and are you saying that a lot of companies still aren't distributed with their data?
I think they're not. I think engineers believe in the magical cloud fairy.
Yeah,
Um, well, we have it all in Amazon East. That's never
yeah,
gone down.
yeah.
Yeah.
Only in
Or we
Amazon.
have it in two AZs.
Yeah.
Alexa, have you ever had downtime in Amazon?
Um, well, actually, I don't use Amazon, but I know it has had downtime.
Every cloud is, I mean, if you,
Yeah, yeah.
this is an interesting Google, go a Google cloud uptime. And there's
Okay.
several reports that show like, oh, here's well, the average uptime for each one. They ain't getting 4 nines.
Yeah.
Yeah.
Yeah, it's definitely good to be considerate, but would you say everyone needs to be distributed?
Not everyone. Again, it's risk versus cost. If you have two data centers worth of infrastructure, you just double your cost, more
Yeah.
likely, or some multiple. Usually, it's around 70% more to distribute to another data center. I think that's the number, but that's more. Um, if you can, and you have to measure your risk. If Amazon goes down for like like for like that one AZ goes down for an hour, which might happen, or if you're in Azure or Google, they all do this. If it goes down for an hour, is that critical? Is that going to ruin our business? No, then don't worry about it. Um, if it's our shopping cart, yeah, I want that online all the time.
Yeah. Hopefully it's not the hour that you send all of your emails to let people know if they've gotten into their college or not.
Yeah, exactly. Well, that was my first experience with that.
Yeah.
There was an AZ that went down into Amazon East. That's why I keep talking about it. And I was running Cassandra across multiple regions, and I didn't even notice that it went down.
Yeah, I mean that's great. So not only is it highly distributed, but it's also highly scalable. How do you achieve that?
Yeah, so that goes to what I was talking about earlier about the way that we distribute data and the token ranges. So each node is responsible for a certain range of data. And if like for instance you have a 4 node cluster, then every node's a bit like is responsible for 1/4 of the data.
Hmm.
That means that if there's all and that quarter of the data is say like multiple terabytes, then each node is going to have a particular amount of load. Let's say you have like 4 terabytes of data and you have a 4 node cluster. All right, every node has 1 terabyte of data plus a replica. So it's probably going to have more like 3 terabytes of data. Um, because it has to, they also maintain replicas for all their neighbors. They're very neighborly, the nodes
Hmm.
are. But that's a replication thing. So let's say that you need, we ran out of disk space, or we need, like, it's getting hammered, like it's just always getting all the requests. How do we scale that? Well, if you double the size of your cluster, then you'll get double the amount of throughput just because you've taken 4 nodes and every node owning a quarter of the data and gone to 8 nodes and every node having 1/8 of the data. So that will just by design get like a half of the load that it got before. And that's that linear scaling. So if we keep adding nodes, it'll keep chunk, it'll keep going up. And that scale is when you're working with a vertical scaling database like an Oracle or a SQL Server, Postgres especially, the only choice you have is to add more server. And sometimes that's not something you can do. Um, so it's and it's also have you gone through the capacity planning exercise where you sit around and you're like, how many users are we going to get?
Something
You
similar.
been- Yeah, I think everyone has been in that meeting at least once where they're like, let's figure out how much of a server we need to buy or how big of an
Yeah, yeah.
instance we need to get.
Yeah.
Ugh.
Fun meetings.
Fun meeting because you're totally guessing. And so what do you wind up doing? You always double or triple it. Like,
Yeah.
because you don't want to be wrong.
Yeah.
Yeah. So with Cassandra, you have the ability to be wrong and it's not deadly. It's
Yeah.
not career ending.
Yeah. That makes sense. So in what cases do we want to horizontally scale versus vertically?
Yeah, horizontal scaling is good for cyclical workloads. Like for instance, we just got through the holiday shopping season,
Mm-hmm.
and all of our Cassandra clusters, especially in our system, were ramping up. Because they're like, oh, we need more load, more coal in the fire. Um, but what's funny is how many of these start tailing back in January and February because they're like, oh, it's over. So with cloud native, we talk about elasticity. It gives you the option for elasticity. But it's also that thing about this horizontal scaling. The advantage is that you don't waste money.
Yeah.
Instead of buying the $100,000 server that you may need, you just buy $1,000 server, and then I'll buy another one if I need more. Or let's go by instance types because no one's buying
Mm-hmm.
servers anymore. You don't have to get the biggest, gnarliest instance. You can get a different instance type and just keep adding those if you need to.
Yeah, I like that. So much easier to scale or scale as needed.
Yeah, and you save money. This is
Yeah.
TCO. This is
Would
this is what makes the boss happy.
would you say Cassandra's relatively cheap to run?
I would love to say that, but I don't because typically people don't put a little bit in it. It's
Yeah.
it's usually their biggest, gnarliest thing. So it's like it, it can be very cheap to run.
Yeah.
But just based on the use cases, it never is.
Because usually this is Cassandra instances are holding a lot of data, right?
A lot of data, they're in the critical path. They're looking for low latency, so very distributed. They're fitting the use case that it's built for, and they're
Yeah.
doing a really good job. But it's not the cheap way to run data.
Yeah. So a lot of times when we talk about databases, we talk about things like the CAP theorem. Can you discuss a bit how Cassandra balances between these?
Yeah, the cap theorem. Well, it fits into this. What is the scaling and why does it work? The consistency, availability, and partition. Those are the CAP. And this is something that Eric Brewer came up with years and years ago. Eric is at Google now, and he was at the time he was at Berkeley. Had some really cool thoughts around like distributed data, like how do we measure those trade-offs, like what's the
Hmm.
trade-offs. So this is kind of a Silicon Valley reference, the iron triangle.
I love
The
Silicon
conjoint
Valley.
trial. Conjoint triangles of success. God, that, by the way, that show is a documentary. It cringes me every time.
It's also hilarious. I mean, obviously, I've actually never worked in California or in Silicon Valley, but it seemed like an interesting time and environment.
That's 100% true. But I mean, I think most engineers will get the jokes, like a whole episode on spaces versus tabs.
I love that episode. I'm so happy you said that. That is such a funny episode.
I mean, and he broke up with his girlfriend because she likes spaces. And it's like, and the normals, not you and me, the normies out there that are like, why did that happen? You're like, kind of then uses spaces.
Yeah. It's such a funny show. I love it. And now that you said that, I want to rewatch it. I was thinking about it the other day too.
Yeah, yeah, I need to get back to it. I was just at reInvent, and the joke around reInvent, and we're kind of diving away from cap. We'll come back. Uh, the reInvent has this thing called replay at the end, which it's this massive party for the people that attend there, those 70,000 friends. And there are so many times people are like, oh, it's Buckmanity.
Yeah, yeah, yeah.
It's real.
Yeah,
Yeah.
yeah. I love the way they make fun and poke fun of the fun like hype parties that people have in tech too. I think a bit of that's died down, which in some ways is kind of sad. Like I kind of some of that
Yeah.
is just funny and fun. Um yeah, like the huge holiday parties and stuff. I miss that stuff, but it's all
Yeah, those
good.
are the good old days.
Yeah.
Maybe they'll be back. And you just have to work at an AI company now to get that.
Yeah, oh wait, you're right. You're right.
Yeah.
That's a
Yeah.
good that's a good
If
point.
Yeah, that'll
Anyways,
be the
cap
next
theorem.
next season of Silicon Valley will be an AI company.
Yeah.
Yeah, so Cap Theorem back when Silicon Valley was in season one, Cap Theorem was around. So the trade-off, the whole trade-off that iron triangle I talk about is like, consistency, availability, partition, pick two. And that was what Eric was like trying to get people to think about and rationalize about whenever they're picking a database, because at the time, well, relational databases, a single server can do all three of those things. Well, and they have a very high consistency. The availability is based on a single server. And of course, there's no partition tolerance, because partition tolerance means like if the two databases can't see each other, if it's a single server, you're okay. So CAP is all about distributed systems. And um, before CAP, there was the Eight Fallacies of Distributed Systems, which is a great read if your listeners want a few moments to just breathe in some reality. So good. But CAP was in that for distributed data. And so when you pick the consistency is hard because it's that's where the most coordination is required. So with Cassandra, like we are what we call a strong AP system. So meaning that it's availability and partition tolerance, like it like I said, hard to kill, but partition tolerance, like you can have nodes that don't see each other for a while, and then whenever they do, they have a little party and resynchronize their data and everything's cool. That's actually a wonderful feature. The consistency, but consistency meaning like if I put data in the system and I immediately read it, will I get the same thing back? Um, in a well-running system without a partition, you Cassandra is a strongly consistent system. But if you are okay with, if you wanted to have to survive a partition event, then you have to sacrifice consistency in that regard. And that's where the word eventual consistency comes in.
Hmm.
It's not that it's broken, it's just a feature of the system that you wanted. That's how you get 12 years uptime. But it's something to plan around, um, especially in distributed systems across geographics, like Europe to North America to Asia.
Yeah, so when you're saying there was one node that survived, or it could be said if there were two nodes but they couldn't talk to each other at the time, then it's still up and running, but maybe it's just not consistent. If you hit one, maybe you'll get one answer, and one you'll get another.
Right. And here's here's the situation that'll probably strike fear in your heart is you have two data centers, one in Asia, one in Europe, and they're both accepting writes. And they may be accepting writes for the same data table, but they can't see each other. What
Mm.
happens when they come back together?
Well, is this what Google claimed to solve with one of their databases?
Eric wrote that paper too.
Really?
Yeah,
Yeah.
that was a spanner.
Spanner, Spanner, yeah.
Well, the way that they quote unquote solved it was they're like, our systems are always online. If you read that paper, it's hilarious. They're like, we don't have downtime. There's no such thing as a partition event.
Okay. Because it did something with the time, and I forget now exactly what it was. But so are you saying that they actually didn't solve it?
They they played pretty. My professional opinion is they played fast and loose with two things. First of all, their ability to keep a cloud online, and the second thing is yes, the time management. So timestamps, they use this thing called Armageddon Master. Can't make this up, and it's a atomic clock. And So they have these really, really high resolution keeping devices in all their data centers that when, and it, Cassandra does the same thing. It uses the last write wins. So they just looks at a timestamp. Then the Cassandra node A looks at Cassandra node B and says, what timestamp do you have on that data? Is it before or after the one I have? If it's before, you win. If it's after, I win. So I'm sorry, the other way around. If it's after, I win. So it's the last right wins.
Mm.
Spanner does the same thing in a lot of ways. Spanner, we could spend a whole episode talking about consensus protocols and what Spanner does as well, because it uses Paxos and two-phase commit in between those. But the timestamp is that's their secret sauce. They've got the nuclear timestamp.
And is Cassandra as a product and Spanner similar in what is trying to achieve in the use cases?
No, they're very different. Spanner is a SQL database that they have built in some mechanisms so that you can work across multiple data centers. And so this is the one of the hardest problems of distributed data is multiple geographies, being able to do multi-data center. There are a lot of databases that Spanner paper described a way to do it with consensus, and like I said, they use Paxos with a two-phase commit between those two. So the problem with coordination is the most expensive thing you're going to do in a distributed transaction. Not CPU, not memory.
To maintain consistency. Yeah.
Yes. And the expense, the dollar sign on the expense is time, how much time it takes.
Which affects availability too, the time.
It'll affect a lot of things. I mean, yeah, it could be availability. I mean, think about like if you're trying to save something in a shopping cart and then you get the spinning beach ball and it's like takes 10 seconds. You're probably not
I
going to shop
can't
there anymore.
I can't get the information until I'm synced if I'm highly consistent. Yeah.
Yeah.
Makes sense.
So yeah, that's pretty hard. And that's the thing about Spanner is that when you do an insert, it takes a long time. When you do a read, it's fast.
Okay. So it's optimized for reads rather than writes.
And they put all of the consistency guarantees into the write. So when they write the data, they put all the guardrails around it to make sure that the data that is written in all the different data centers is exactly the data. So then the reads are just kind of whatever. And yeah.
Okay. And for Cassandra, is there typically an expectation that the use case will have more reads or more writes, or does that not matter?
We try to balance both, but what we don't do is we don't do a stop the world for a write to be consistent. We use mechanisms like quorums and we actually hand it to the user. It's a tunable consistency. So, you, Alexa, you get to choose what you want. If you want it to be pretty loose, like a consistency of one, meaning that only one replica acknowledges the write,
Yeah.
which is fine for like log data, that kind
Mm-hmm.
of stuff. It doesn't mean that it won't ever get written to the other ones, but this one will. That's up to you. But if you want it to be strongly consistent, you can use quorum. But the thing about quorum is that now you have to understand that if you have a partition or something like that, that it may not satisfy the quorum.
Okay. Yeah. So you have to just set it to the configuration that's appropriate for a use case.
Yeah, and yeah, and it's up to you. And there's ways that you could fail back or change things. But like I said, Cassandra gives you plenty of ways to shoot yourself in the foot if you want to. But we give the configuration to the end user. It's up to you to tell, you have to tell the system how you want it to go.
Nice. So what are some advancements coming up in Cassandra that you're excited about?
I'm glad you asked because it's about consistency.
Nice.
Yeah, I think probably the main complaint at this point in 2025 that I hear most about Cassandra is it doesn't do an ACID transaction. And yeah, sure, ACID transactions are very important, especially when you're dealing with moving data from one point to the other, and you need that guarantee. Cassandra can do all of the letters A, C, I, and D, just not all together. And so we have a protocol that's probably been worked on for about past 5 years by a group of engineers at Apple. It's called Accord. It's amazing. It's not just in Cassandra land, in the distributed computing world, it's starting to make waves because it is really the next generation. And so Spanner was a paper that was, I think, 2011, 2012. Raft was around the same time. And then later there was the Calvin paper, which some databases evolved to. So there was these, like, and if you look at Spanner, Spanner launched databases like Spanner and Cockroach DB, for instance, and Yogabyte. There's databases that use the Spanner paper. With some modification. Calvin, there's, I think FaunaDB uses Calvin. So those are all based on a paper, a scientific paper or computer science paper about consensus. Well, Accord is the next generation above that. And that's what's going to be in Cassandra.
Oh, awesome.
And the problem that it's trying to solve is this really hard problem of maintaining low latency with an ACID transaction that spans multiple data centers. And like I said, when you insert data into Spanner, it takes a couple hundred milliseconds sometimes. That's
Okay.
a long time. But we don't want to. We could have used Spanner. We talked about it. We didn't use it. We didn't use Raft. I have a talk about all the things we looked at and we rejected because what they would force us to do is if we adopted that protocol, then it would have invalidated the core tenet of Cassandra. Like that linear scaling, multi-data center, high resilience.
So how is this new protocol basically working?
So how it works is it takes advantage of the way Cassandra works by, all right, every rep or every token around a node, it's like a node has a token range that you're like, oh, this is how much data I have on it, and here's my replicas. That's the domain of the data that you need to worry about. It's not the entire cluster. So instead of doing like a full cluster lock to lock everything down to do an ACID transaction, it only does a lock on one thing. And so like on one stretch of data, and it only has to coordinate between 3 nodes if there's a replica of 3. But it also uses a really clever way of timestamping that are very important, because in a consensus protocol, there's 2 things. There's a serializability and then there's linearizability. And that's a hard word for me to pronounce. But to be linear means that one thing happens after another by time clock. And think about like a bank transaction. Bank transactions, I put in money, then I took out money, and then I put in money. And there's like things that happen. So it's ins and outs and ins and outs. If you get that order wrong, that could end up pretty bad. Like before you put any money in, it'll take it all out.
Yeah.
Like, wait, no. So that's and that's hard. It's really hard to do. So keeping the clocks going. But for the end user, it's a simple interface. You just use a command that says, hey, inside this transaction, do these 3 things and make sure that it's exclusive. So I think it's going to change a lot of perceptions. I'm excited.
That sounds exciting. So that's in progress. When will it be out?
So I have a Docker build actually on my Docker Hub of the beta. Well, it's not even a beta. It's like pre-alpha. It's a branch right now. So we're looking at releasing this in the next version of Cassandra, which I think will be Cassandra 6. But it's available out there in the repo. You can go look at it if you want to build Cassandra. But yeah.
Awesome.
Yeah.
Cool. Well, that sounds exciting. That's all the questions I have. Do you have any last words or piece of advice for our listeners?
Come out and find us. We're a pretty open community. So, I'm on LinkedIn. You can connect with me pretty easily. If you want to send me a DM, ask me questions, I'm always open for it. So yes, join our community. We would love to have you.
Great. Thank you so much for your time. And I'll make sure to add some links to how to join the open source community in the description as well.
Great. Thank you, Alexa.
Thank you. Thank you for listening to this episode of Alexa's Input. Make sure to subscribe so you know when the next episode comes out. Also, you can follow me on Twitter at Alexa's Input. Finally, any donations are welcome. You can go click the link in the description, go to the Anchor page, and I do take donations because I edit and record these podcasts on my own. So those are very much appreciated. Thank you, and I'll see you next time.